Hello everyone, today, it's my pleasure to introduce a review, maternal and infant gut microbiome. Early life gut microbiome assembly is a pivotal determinant of lifelong health, yet integrated frameworks across developmental stages remain incomplete. This review systematically outlines host microbiome interactions across 4 continuous stages: preconception, pregnancy, postpartum, and early childhood. The highlights of this review are: first, maternal and early life microbiota participate in host developmental programming. Second, dysbiosis during critical windows may affect immune, metabolic, and neurodevelopmental trajectories. And third, this review discusses the future direction of microbiome-based precision medicine. Figure 1. The maternal gut and vaginal microbiota shape endocrine balance, inflammation, and the implantation environment. Paternal microbiota may also contribute to offspring risk through sperm quality and epigenetic changes. Figure 2. Across the 3 trimesters, gut-derived indoles, short-chain fatty acids, and bile acids signal through the placenta to regulate immune tolerance, vascular remodeling, and nutrient transport. When these signals deviate from the adaptive range, the risk of pregnancy complications may increase. Figure 3 shows the establishment of the infant gut microbiota during birth and early postpartum life. Delivery mode is the key ecological event that introduces founder microbes into the infant gut. In early postpartum life, breastfeeding, skin-to-skin contact, and antibiotics jointly shape the direction of microbial succession. Figure 4. The preterm gut microbiota reflects the combined effects of host immaturity and intensive clinical exposure, which can promote opportunistic pathogen expansion, insufficient bifidobacterium colonization, and depletion of beneficial microbial metabolites. Figure 5. Staged succession and functional maturation of the early life gut microbiota. Infant microbiota progresses from pioneer colonization to breastfeeding-driven bifidobacterium dominance, then to complex carbohydrate utilization after weaning, and finally toward a more stable adult-like ecosystem. Figure 6. The gut-brain axis. Gut-derived metabolites can influence microglial maturation, myelination, blood-brain barrier integrity, and synaptic plasticity. Therefore, early microbial disruption may be associated with neurodevelopmental disorders. Figure 7. Gut microbes support barrier maturation, mucosal IgA responses, and immune tolerance. Perturbations related to caesarean section, antibiotics, or formula feeding may increase inflammatory and allergic risks. Figure 8. Healthy maternal-infant coevolution supports growth and metabolic homeostasis. In contrast, malnutrition, infection, caesarean section, antibiotics, or a high-fat diet can push the microbiota toward an immature or metabolically shifted state. Figure 9. A critical window reflects whether host developmental needs meet microbial functional signals at the right time. Some processes may be difficult to reverse once missed, whereas others can still be recalibrated by nutritional and microbiome-based strategies. Figure 10. The translational framework includes 3 steps: identifying and validating biomarkers, developing safe and controllable candidate interventions, and moving toward clinical implementation through rigorous trials, standardized testing, and long-term follow-up. In summary, this review emphasizes that the maternal-infant gut microbiome is a functional ecosystem spanning early life. It proposes a developmental synchronization framework, in which the key issue is whether microbial functions and metabolic signals match host developmental needs at the right time. This perspective may support, more precise microbiome modulation strategies.